And so for part C, we're asked to obtain an expression for the electric field in the region R less than or equal to big R. So basically we have to find the electric field for anywhere that is for a charge that is anywhere inside the volume of the sphere. And you'll notice that we'll have to use Gauss's law once again to find the electric field, but because we have the same exact surface area, the surface area of a sphere, we'll have the same exact electric field expression, but with a little bit of a twist. For part C, our electric field will in fact equal Q enclosed. Notice I'm putting the enclosed because we're not sure what that enclosed charge is, divided by 4 pi little r squared times epsilon naught. So you'll notice it's the same exact thing as our other expression, except that we don't know what the Q enclosed is at this point. And to find the Q enclosed, we'll do exactly what we did in part A actually, which is what we did in part A was we integrated from 0 to big R, which was the radius of the entire volume, in order to find the charge. Whereas this time we're just going to integrate from 0 to little r, which is going to be inside the volume. And so we can actually just look at this and just change our integration limits, and we'll come with an expression for the Q enclosed. So here we can write that Q enclosed is equal to, actually just go back and look at it, rho naught times 4 pi. Rho naught times 4 pi times the integral from 0 to little r, most important part of this, times r squared minus r cubed divided by 4 dr. Now, because this integration is similar to the one that we did in part A, and also in the interest of time, I'm going to just give you the solution to this integral. It's a simple integral, and you can do it yourself because it's very similar to the one that we did in part A. And so the solution is going to be Q times little r cubed divided by 4, nope, not 4, times little r cubed to the quantity 4 minus 3 times little r divided by r. And since this is our Q enclosed, we can divide this by 4 pi little r squared epsilon naught, which is going to be our electric field, as we found from this equation right here. So our electric field in the end is going to be equal to Q times, after a little bit of simplification, of course, I'm not going to do those steps either, because we did them earlier as well, Q times R divided by 4 pi epsilon naught times big R cubed times the quantity 4 minus 3r little r divided by big R. And that is our electric field. So now we can go on to part D. And part D says, graph the electric field magnitude E as a function of R. Alright, so basically just taking this function, making it as E as a function of the radius, or the arbitrary point, and we have to graph it basically. And so we have to make some observations about what this graph is going to look like first. It's going to be R, it's going to be E of R. And what we have is that this equation here, as we found earlier, only holds for when R is less than or equal to big R. So therefore, our graph, this equation will only hold from 0 to the point where we have reached big R. After that, another equation will hold. And what equation is that? That's the electric field of part C of part B for this one, because this electric field here told us the electric field for anywhere outside the sphere of that was given to us. So therefore, that's going to be E, the Q divided by 4 pi r squared. We're going to put that off to the side right here. E of r equal to Q divided by 4 pi r squared times epsilon naught. So let's leave this aside for now and graph from 0 to where the radius of the actual sphere is. So to make this equation right here a little bit simpler, let's just say that that's E, just to make it more visually pleasing, we'll make this E equal to, and since the variable is r, we'll distribute the r, and we'll call all of this, just call it k. Just for now, we'll just call it k, just to make writing easier. We'll call it, so the formula, the equation is 4r minus 3r squared divided by r. And mathematically speaking, what kind of an equation is this? This is a parabolic equation. And so we know that what's going to happen is that we're going to start from 0, we're going to, since this is negative 3r squared, it's going to be something of that sort, where we have to, and something of this sort, and we don't know where it's going to be exactly. So we should basically, anyway, the first step to do in solving a parabolic function is to find the roots. So obviously, if we just ignore that k, we know that the roots are going to be anywhere where r times 4 minus 3r divided by r is equal to 0. And remember, this is just straight from math class. And so this will always be 0 whenever the outside r is 0. And so that makes sense, which means that our function will start at 0. And whenever that inner function is 0. And so therefore, after doing a little bit of algebra, you'll notice that you can bring the 4 over, and then you can multiply them by, so basically you do 4 minus 3r divided by r. And whenever he's equal to 0, this whole function will also be 0. And so therefore, when you do some algebra, you'll do 4 over 3, because the negatives will cancel, times r, big R, will be equal to little r. So whenever r is equal to 4/3 of big R. And so we know that the root, so that's 4, so actually let's examine that. 4/3 of r means that we're going beyond the radius of r. And of course we said that this function does not hold for outside of r. So therefore what's going on is like this. When we reach, when our parabolic function will reach r, we'll stop him right there. Because we know at this point this function does not exist. This is supposed to be parabolic, nothing weird going on here. And so that makes everything a lot easier. And so we can just go to this equation right here to find what's going on after we pass the radius. And all that this equation is simply some constant q divided by 4 pi epsilon naught, and we'll just call that k, 1 divided times 1 divided by r squared. And so what is this? What is the limit as r approaches infinity for this function? It's going to be 0. And so at this exact point, he's going to start to fall off as it approaches infinity. And that makes sense. As you go farther away from the point, from the charge, the electric field is going to be much smaller. And so the last part of the problem, almost done. which is a perfect question to end the problem. Find the value of r at which the electric field is maximum, and find the value of that maximum field. And so we should know from first semester calculus courses that in order to maximize or minimize a function, all we have to do is take the derivative of that function, set it equal to 0, and then solve for r. And so if we take our equation and find the derivative of it, set it equal to 0, it's going to be equal to some constant k times 4 minus 6 little r divided by r. And if you set this all equal to 0, the k will go away. You'll be left with little r equal to negative 4 divided by negative 6, which is just going to be 2/3 of r. And so therefore this point right here is the electric field reaches its maximum 2/3 of the way to the edge of the surface, to the surface of the sphere. And what exactly is that electric field? Well, we plug it in. It's r. Now, since the rest of this problem is just plugging in 2/3 of r into this equation right here, to this equation, I'm just going to go ahead and give you the answer because I'm trying to save a couple more minutes for my time limit, and that answer is going to be equal to q divided by 3 pi epsilon naught times r squared. And of course all that value is, just to recap one more time, is the maximum value of this function right there, which we just found is to be q divided by 3 pi epsilon naught times big R squared.